my name is Stuart Hill, and I'm here to guide you through this module. This is the second of a series of modules in which we will introduce you to the concepts, technology, and functionality provided in the GE JunglePAX platform. In this module, we will be covering a basic introduction to networking concepts. In addition to reviewing the concept of a network in its various forms, we will be investigating the differences between hubs, switches, and routers, as well as providing a brief introduction to network routing protocols and quality of service. The first section of the module describes a network. What is a LAN, MAN, or WAN, and what transport technologies are typically employed there? A network uses a collection of networking technologies to provide connectivity between a group or groups of computers and servers. These groups may be local or geographically distributed. The size and dispersion of these networks determines the name associated with the network units. A local area network, referred to as a LAN, is typically restricted to computers and/or servers within a small area such as an office, school, home, or building environment. Network speeds typically range from 10 megabits per second to as high as 100 gigabits per second and may employ wireless or Wi-Fi technologies. A metropolitan area network, referred to as a MAN, covers a larger geographical area than a LAN. A MAN can be as small as a couple of city blocks, or it can be as large as the entire city and surrounding areas. Network transport technologies found in a MAN can range from frame relay to SONET to OTN or gigabit Ethernet. Ethernet network speeds of a MAN can typically range from 1 gigabit per second to as high as 10 or 40 gigabits per second on fiber optic cable. A wide area network, referred to as a WAN, covers a very large geographical area. A WAN can interconnect several metropolitan area networks, or it can be as large as a global network like the Internet. Network transport technologies found in a WAN can range from frame relay or SONET to OTN or gigabit Ethernet, but may make use of satellite-based wireless technologies as well. Satellite transport speeds typically range from the kilobits to megabits, but are subject to significant latency not typical of terrestrial services. Terrestrial Ethernet network speeds of a wide area network typically range from 1 gigabit per second to 10 gigabits per second on fiber optic cable, but with newer optics available today, they can go as high as 40 gigabits per second, similar to that of a metropolitan area network. SONET, synchronous optical networking, and SDH, synchronous digital hierarchy, are two TDM or time division multiplexed protocol technologies found in high-speed wide area networks. Their transmission rates scale from as low as 51.84 megabits per second to as high as 160 gigabits per second. SONET SDH is a transport protocol in that it allows for the transport of many different circuits within a single framing protocol. The basic unit of transmission for SONET is an STS1, which has a rate of 51.84 megabits per second. The basic transmission unit for SDH is an STM1, which has a rate of 155.52 megabits per second. Multiple units can be aggregated by time division multiplexing to form higher transmission units. For example, 3 STS1s can be multiplexed to form an STS3, and 4 STS3s can be multiplexed to form a 622.08 megabit per second OC12 or STM4. SONET SDH networks are synchronized across the entire network through the use of atomic clocks, as consistent clocking is a requirement of synchronous networks. A key component of SONET SDH is that it also includes in-band operations, administration, and management functions used to manage and monitor the health and performance of the network. OTN is a fiber optic-based WAN technology that was designed to support the use of wave division multiplexing within the optical network. The core function of OTN was to provide the capability to carry digital circuits on optical channels. Similar to SONET SDH, OTN has a hierarchy of transport units used to carry these digital circuits. An optical transport unit, or OTU, is the higher data structure into which optical data units, or ODUs, are mapped. An OTU scales from an approximate rate of 2.66 gigabits per second, capable of carrying a SONET OC48, to an approximate rate of 112 gigabits per second, which can transport a 100 gigabit Ethernet signal. Each OTU is designated as an optical channel or wavelength. An ODU can scale from as small as 1 gigabit per second to as high as 100 gigabits per second. OAM in OTN is much the same as OAM for SONET SDH, but allows the added capability of association of the OAM to each individual wavelength. OTN is designed to provide transport for SONET SDH, Ethernet, fiber channel, packets, or other OTN signals. WAN Ethernet is the transport technology employed by the JunglePAX platform. WAN Ethernet is a synchronous Ethernet transport technology that is compatible with SONET OSI 192 or 9.953 gigabits per second at the WAN-PHY or physical coding sublayer of the interface. The basic transmission units of WAN Ethernet range from 1 gigabit per second to 100 gigabits per second. A WAN interface sublayer, or WIS, is employed to frame the data stream into the OSI 192 compatible frame, which provides access to some SONET overhead features and many of the OAM benefits seen in SONET SDH. When combined with RFC 1588 or Precision Time Protocol, Synchronous Ethernet or WAN Ethernet is now able to provide support for clock transport. Now that we have covered the basic network topologies, we'll discuss how information is exchanged between hosts within the network topology. When an application runs on a device, a series of protocols are employed to package up the information needed to be exchanged between the device and the remote endpoint of the conversation. These protocols are referred to as layers in the overall process of packaging that information for transmission. Presented here are the 7 layers of the OSI or Open Systems Interconnection Communication Model, commonly referred to as the 7 layers of the OSI stack. Each layer represents a distinct and unique component required to process and encapsulate datagrams for communication between network-attached endpoints. As an example, all 7 layers of the OSI model are employed to get information to your desktop web session from the web server on the Internet. The panel on the right side of your screen provides examples of each layer in the OSI model. For this course, we will focus on the Layer 2 and Layer 3 components of the OSI stack involved in communication on an Ethernet-based network. Every network interface card in an Ethernet network must have a Layer 2 MAC or Media Access Control address. A MAC address is composed of 6 bytes. The first 3 bytes typically identify the manufacturer of the network interface card, and the last 3 bytes are usually from a range specific to that manufacturer. Although modification of a MAC address is permitted on many devices, MAC addresses are required to be unique within specific network domains so that communication can be supported between designated hosts. Within Layer 2 domains, MAC addresses are used to identify source and destination addresses for packet forwarding. Within Layer 3 networks, IP or Internet Protocol addresses are employed. The 2 primary forms of IP addresses are IP version 4 and IP version 6. An IP address is identified by a bit-based value with a matching bit length mask used to signify which portion of the bit sequence represents the network address and which portion represents the host within the network. An IP version 4 address is composed of 32 bits and is represented by 4 8-bit byte values separated by periods. Within an IP version 4 network, all zeros within the host bits is referred to as the network address. The all ones host address is referred to as the broadcast address and is used to address packets to all hosts within the network. The number after the slash is called the network mask and designates the number of bits from the left that form the network portion of the address. The remaining bits represent the number of hosts that are addressable on that network. For example, with the network address 192.168.23.1/24, the network portion of the address is the first 24 bits, 192.168.23. The last 8 bits remaining represent the specific host address. In this case, there are 8 host bits remaining. This means that there can be 254 hosts, with host addresses ranging from 1 to 254. For cases where a network mask is required, separately in a configuration, it is described as the all ones 8-bit value of the network portion of the address, as shown here. An IP version 6 address is composed of 128 bits and is represented by 8 16-bit values in hexadecimal separated by colons. A common shorthand notation is to represent a single extended sequence of 0 values with a double colon, as shown in the example. Note that the example is identifying a single host address. We know this because the network mask is all ones, in this case 128 bits. As with IP version 4, IP version 6 addresses still have network and host portions and have ranges of address blocks for designated uses. IP version 6 address space introduces scope-based ranges and replaces broadcast functionality with multicast to avoid disturbing all interfaces in a network. Within IP version 4 space, specified address ranges or blocks have been set aside for designated uses. Two examples of these ranges are addresses for internal private networks only and for multicast traffic. Internal addresses are address ranges specified in RFC 1918, which are not permitted to exist in the global Internet. Multicast addresses are for packets addressed to multiple subscribing hosts within a multicast domain and are used for applications like pay-per-view TV. This slide shows 3 examples of IP address blocks that have common meaning between IPv4 and IPv6. A loopback address is used by applications that need to communicate entirely within the platform on which they're running. A unique local address in IPv6 can be considered roughly equivalent to RFC 1918 IPv4 space, as it is designating IP address blocks that are not to be used in the Internet. Rather, these blocks of addresses are for private use inside home or enterprise network environments. A link-scoped unicast address is restricted to directly connected interfaces. It is not permitted for an address of this type to be used for traffic that is directed beyond a locally attached neighbor interface. Each of these address blocks have a specific scope restriction. The common IPv6 scopes are shown in the bar on the right of your screen. In this chapter, we'll dive into the world of packet forwarding platforms. We'll briefly highlight the functions of hubs, switches, and routers to build a base understanding of the concepts involved. This will be a core component of understanding for the discussion on MPLS and MPLS services later in this course. Having a basic understanding of the structure of an Ethernet packet will make it easier to understand each progressive step of technology implementation on Ethernet and how the packet forwarding function is impacted. Let's have a basic look at what the Ethernet frame includes. The layer 1 components of an Ethernet packet are the preamble and starter frame delimiter. The preamble is a 7-byte sequence of alternating ones and zeros used by Ethernet devices to synchronize their receive clocks. Immediately following the preamble is the starter frame delimiter. It is a specifically reserved pattern used to identify the start of an Ethernet frame. Next, at the beginning of the layer 2 Ethernet frame portion of the packet, you will find the MAC address of the host this packet is addressed to, followed by the MAC address of the host who originated this packet. The ether type field identifies both that this is an Ethernet packet and the type of protocol format to expect inside the payload. The actual payload of the packet follows the ether type field with sizes ranging from 42 to 1500 bytes for standard frames. Non-standard frames can be much larger. Completing the layer 2 frame is the frame check sequence field. This is a 4-byte or 32-bit cyclic redundancy check used to detect instances when packets have been corrupted. When you lay out all 7 components, you get the standard Ethernet frame as shown. In the early 1980s, the Ethernet hub was developed. It is a multi-port network device used to connect Ethernet-attached devices at speeds of 10 megs to as high as 1 gigabit per second. In some environments, hubs are used to extend LANs by interconnecting hubs. The biggest challenge of a hub is that it is a device that repeats Ethernet packets to all attached interfaces on the hub. In a hub, there's no forwarding decision other than sending the packets to all ports. A hub doesn't apply any filters and doesn't pay any attention to packet content to determine how to forward the packet within the LAN. Like the party line telephone services in the late 1800s and early 1900s, a hub sends packets to all ports to all devices attached to the hub ports. The problem with the party lines is that there was no flow control. The hub does not control the timing or propagation of packets between ports. This results in collisions. As soon as you have more than one computer on a hub, you have the opportunity for packet collisions resulting in data loss. As with phone conversations, each device involved in the conversation needs to apply rules dictating that when collisions are seen, a random amount of time is waited before trying to resend the lost packet in order to reduce the probability of having another collision. With each additional computer attached to a hub, you increase the likelihood of collisions. To be able to scale to large numbers of devices and higher data rates, a better way of communication is required. The challenge would seem to be to reduce the number of endpoints in the room, or LAN. By taking the crowd of people and moving them into different rooms, you reduce the chance of conversations colliding with each other. In the networking world, each room, or LAN, would be considered a broadcast domain. Once each conversation has its own LAN, the chances of an uninterrupted conversation are greatly increased. Having a LAN for each and every conversation, however, is not all that realistic. There needs to be a way for each endpoint to have private conversations within the same LAN. It's not desirable from either a security or network performance efficiency perspective to have every packet sent to every port on the hub. An Ethernet switch provides isolated, dedicated connectivity to each port-connected device within a common LAN. Packets are forwarded based on learned MAC addresses. Packets received on an interface destined for MAC addresses that have not yet been learned by the switch are broadcast to all ports on the switch. Whenever an Ethernet packet is received on a switch port, the port learns the source MAC address of the device that transmitted the data packet to the port. Once the destination endpoint device responds to the initial packet, the switch will now learn the MAC address of that device. Since the switch has now learned both MAC addresses, all future communications between the two devices will be switched directly between the two affected ports only. Because packet flow is restricted to learned MAC address destinations, switches do not suffer from the same collision and port bandwidth utilization based issues found in hubs. This solves the problem of direct communication between communicating partners, but does not, however, solve the issue of limiting the scope of broadcasts of packets for unknown MAC address destinations. Conversely, there are times when we want to prevent devices from being able to communicate, but we don't want to buy and deploy a separate switch or LAN for each scenario. In addition, separate switches would mean a requirement for multiple network interface cards for devices that need to talk to each domain, or LAN. For scalability, it would be preferable to be able to use a single switch to be able to connect devices, but control the exposure of each device to multiple LANs on the switch. A VLAN can be used to create multiple LANs within a single switch. A VLAN is a virtual LAN. Each VLAN is a self-contained broadcast domain. Broadcast packets are only relayed within the VLAN in which they are received. A VLAN-capable switch can contain many VLANs. Only devices on ports listed as members of the VLAN are able to communicate with one another. Each VLAN on a switch has an identified list of ports as members of that VLAN, and each port can be a member of more than one VLAN. However, for a port to be a member of more than one VLAN, it has to be defined as a trunk port supporting VLAN tagging. Where a port is a member of more than one VLAN, packets entering and leaving the port for each VLAN have a VLAN ID embedded in the packet. This VLAN header is described in the IEEE 802.1q networking standard. The VLAN tag is a 4-byte field inserted into the Ethernet frame between the source MAC and Ethertype fields. Okay, so where are we? Virtual LANs provide us the ability to break up broadcast domains into segments. MAC learning with Ethernet switching allows restriction of communication flows to just the hosts involved in the conversation. What we've done so far allows us to communicate between hosts at layer 2. What do we do when two hosts on two different VLANs wish to communicate with each other? To communicate between two layer 2 broadcast domains, layer 3 networking is used. In addition to MAC addresses used for Layer 2 forwarding, IP addresses are used to designate source and destination addresses for Ethernet packets for Layer 3 forwarding. Each broadcast domain, or VLAN, is assigned an IP network address. Each device, or host, is assigned a host address within the local IP network. A router is a device which forwards traffic between two or more directly connected Layer 3 networks. Each interface on the router connected to the directly attached IP subnet is assigned a host address within the subnet. This host address is known as the gateway for the local subnet to use to reach networks external to the local subnet. As you can see, insertion of a router between two Layer 2 broadcast domains and assignment of IP subnets to those VLANs allows communication between two previously isolated networks. However, a router will only forward information based on knowledge of attached or reachable networks. Packets received by a router containing destination addresses that the router doesn't know will not be forwarded. Many network devices sold today actually combine routing and switching functions into a single chassis. How does a router know where to find IP subnets that are not directly attached? Each router can be manually configured to identify where subnets are and which ports to use to reach them. This is called static routing. For networks relying on IP reachability, this doesn't scale. As the number of routers in a network grows, so does the complexity of configuring all the combinations of static routes. In addition, changes to network state as a result of link disconnections or failures can result in significant changes to network topology. In order to simplify the job of exchanging reachability information, routing protocols are used. In this chapter, we will introduce routing protocols. What do they do? And we'll give a brief description of the two main camps and where they're used. Please note that this is merely intended to provide a high-level summary of routing protocols and their purpose. Detailed coverage of routing protocol function, configuration, and troubleshooting is not a core focus of this curriculum. A routing protocol is a method by which two or more routers exchange route reachability information. The algorithm associated with each individual routing protocol determines how that protocol chooses which routes are to be used to reach each IP subnet in the network topology. Three examples of IP routing protocols are static routes, RIP, which is Routing Information Protocol, and OSPF, which means Open Shortest Path First. The size and composition of networks fall into three main categories: intranet, extranet, and internet. An intranet is a network built with the purpose of sharing information amongst users within a single organization such as a company. An extranet is a carefully controlled access to an intranet from outside the corporate network. This can include remote access to corporate assets by mobile employees or external companies or suppliers. The Internet is a global network commonly used for accessing information in an open, unrestricted manner. The routing protocols operating inside an intranet are commonly referred to as interior gateway protocols. These routing protocols exchange routing information within an autonomous network. Examples of an IGP or interior gateway protocol include RIP, Routing Information Protocol, OSPF, Open Shortest Path First, and ISIS, Intermediate System to Intermediate System. Exterior Gateway Protocols, or EGPs, are found in extranets and the Internet. The protocol that operates in this domain is known as BGP, or Border Gateway Protocol. BGP operates by exchanging routing information between multiple autonomous networks. The methodology by which routing protocols select paths to a destination can be divided into two camps: link state and distance vector. Link state algorithms compute the best path to a destination based on a calculation involving the state of each link and its metric or cost. The path resulting in the least cost is chosen. Distance vector algorithms compute the best path to a destination based on the number of hops and the interface used to reach the destination. Typically, a router executing a distance vector algorithm will build a picture of the network based on their neighbor's view of the network, whereas routers executing a link state algorithm will construct their own view of the network based on information regarding link states propagated to them by their neighbors. The table shown describes the main differences between the link state algorithm OSPF and the distance vector algorithm BGP. OSPF networks are typically broken into areas within which discovered neighbors exchange link availability and cost. As mentioned earlier, the link states and costs are used to compute a reachability matrix from each router's perspective. When combined with the short intervals for hello heartbeats, the algorithms used for link status updates and path computation result in very fast convergence in times of network change. As an EGP, however, BGP exchanges information at the autonomous system level and uses autonomous system paths to determine preferred routes. BGP is also unique in the fact that it can operate as both an internal border gateway protocol and an external border gateway protocol in the sense of IGP versus EGP. BGP has access to the tools of next hops, communities, and preferences as methods by which route selection and route identification or grouping can be managed. As we will see in later chapters on MPLS, these tools are very handy for exchanging MPLS service reachability. Before concluding this module, we will take a quick look at quality of service. We will present a brief description of the main components of quality of service and how it's used in the JunglePAX. In an environment where the network must have the capability to handle applications of different priority, quality of service can be thought of as the ability to provide differentiated levels of service to different applications. This is reflected in the overall service level experienced by an individual data flow from the time it enters the network to the time it leaves the network. Class of service is the mechanism implemented in each network node to classify, remark, and service data flows transiting the individual node. Quality of service is most commonly known as a congestion management tool. Traffic of varying priorities is prioritized into distinct queues with specific scheduler configurations to ensure priority traffic is processed and forwarded at the cost of lesser priority traffic in times of heavy congestion. In the example shown, corporate and voice-over IP traffic, prioritized as best effort and important respectively, are sacrificed in favor of the more critical energy management traffic. A key benefit of QoS that is frequently overlooked is its ability to provide service consistency through queue management. Traffic in higher priority queues are guaranteed a more consistent pattern of service such that jitter is contained to reasonable values. Appropriate distribution of memory buffer resources to lesser priority queues increases each queue's ability to reduce packet loss during times of bursty traffic. This slide describes the lifecycle of a packet as it enters and/or leaves each node in the path. As packets ingress the node, their priority markings are inspected for priority-based classification and treatment. As packets are forwarded to their appropriate egress interfaces, they are placed into queues in accordance to the identified priority and treatment. Packets waiting for the scheduler to service their queue are associated with specific drop profiles which determine the packet discard probability in relation to the fullness of the queue. Queues experiencing high volumes of traffic can be managed using scheduled windows of service and weighted random early discard measures which are used to manage queue fullness in times of congestion. Typically, each egress interface contains 8 queues. The JunglePAX also is initially set up to handle 8 internal priorities mapped to 8 priority queues on each WAN port. As packets egress the node, marking schemes are applied to mark packets according to the priority to which they've been assigned. This allows the next node to inspect the priority marking for classification and further priority-based treatment. In a classical deployment of QoS, the 8 priority queues have a priority value increasing from 0 to 7, represented by 3 bits, with 0 being best effort or routine, 5 being critical, and 7 network control. For reasons that will be explained in full detail in later modules regarding the JunglePAX and MPLS-TP, the JunglePAX deviates from this scheme. It should be noted that although the JunglePAX ships with this modified configuration, it is still possible for it to be modified using the provided user interaction methods. Because the JunglePAX does not rely on control plane technologies to function, the sequence of priority definitions has been modified to more closely address the needs of applications and environments in which the JunglePAX will be deployed. The JunglePAX places critical traffic as more important than network control. In addition, it defines two classes of critical, again above network control, that differentiate between TDM-OP and Ethernet source traffic. TDM-OP traffic has the ability to be prioritized into queues 7 and 5 in order to provide priority differentiation within TDM source packet streams while maintaining relative priority over non-TDM traffic, sharing priority with network control traffic. Ethernet traffic is defaulted to have access to queues 0 through 6 in order to provide a condensed but full-featured quality of service environment to Ethernet source traffic as well. Thank you for watching this module. In this video, we've reviewed the base components of LAN and WAN networks and provided a foundational understanding of routing protocols and quality of service.